Data types: null, undefined, Boolean, number, string, object, symbol, big int. JavaScript variables can hold different types of data. Some of the most common data types are null, undefined, Boolean, number, string, object, symbol, and big int. Each data type serves a particular purpose and helps developers manage and manipulate data efficiently. Numeric values are represented by the number type. Textual data is covered under the string type. The null type is a special keyword denoting a null value, indicating the intentional absence of any object value. Undefined indicates that a variable has not been assigned a value. Boolean values are represented by the Boolean type, having two values, true or false. Objects are collections of properties, and the object type is for complex data structures. The symbol type is used for unique identifiers, and big int allows the representation of integers larger than 253-1, the largest number JavaScript can reliably represent with the number type. Type coercion. Type coercion in JavaScript is the process where the engine automatically or implicitly converts values from one data type to another, such as strings to numbers, when it is required by an operation. Understanding how it works is crucial to avoid unexpected bugs in code. In the first line, JavaScript concatenates the string 5 and the number 3, resulting in the string 53 due to string coercion. In the second and third lines, the operands are coerced to numbers, resulting in arithmetic operations. 5 minus 3 gives 2, and 5 2 gives 10. In the fourth line, true is coerced to 1, since true is 1 and false is 0 in numerical context, so true plus 2 evaluates to 3. Lastly, the equals operator performs type coercion, treating the string 5 and the number 5 as equal, thus returning true. Each scenario exemplifies how type coercion can affect the outcome of operations in JavaScript. Topic: equalsync, equality comparisons and sameness. In JavaScript, equals and equalsync operators are used to compare two values, but they don't work in the same way. Understanding their differences is crucial for writing precise and bug-free code. The code compares the string 5 with the number 5 using both equals. The first comparison, equals, returns true because equals performs type coercion, converting both values to a common type before comparing them. In contrast, the second comparison, equals, returns false as it checks for both value and type equality. Is known as the strict equality operator and doesn't perform type coercion. It's generally recommended to use equals for comparisons in JavaScript to avoid unexpected results due to type coercion. Scope and hoisting. Scope defines where variables and functions are accessible within your code. JavaScript has both global and local scope. Hoisting is JavaScript's default behavior of moving declarations to the top of their scope before code execution. In this example, var x equals 5 is hoisted, allowing console.log x to output undefined instead of throwing a reference error for x not being defined yet. Function test demonstrates local scope. Variable y, declared inside test, is not accessible outside of it, leading the console.log y outside of the function to throw a reference error. This showcases both how hoisting applies to variable declarations and the difference between global and local scope. Var, let, and const. Understanding var, let, and const is fundamental in JavaScript. These are keywords used to declare variables, each with its scope, lifespan, and mutability. Var declares a variable that is function scoped or globally scoped, and it can be updated and redeclared within its scope. Let introduces a block-scoped variable that can be updated but not redeclared in the same scope. Const is similar to let in terms of block scope, but it cannot be updated or redeclared. Once a constant is assigned, it holds that value for its lifetime. Understanding these differences is crucial for managing the accessibility, mutability, and lifespan of your variables effectively. Function declarations versus function expressions. In JavaScript, functions can be defined in several ways, each with its own nuances. Two primary ways are through function declarations and function expressions. Understanding their differences is crucial for mastering JavaScript's behavior and scope handling. A function declaration is hoisted, meaning it can be called before it's defined in the code. This phenomenon allows for more flexibility in code organization. The Hello World function exemplifies a declaration. On the other side, a function expression, like the greet function, is not hoisted. A function expression is assigned to a variable and can only be called after its definition. These differences emphasize the importance of understanding scope and hoisting in JavaScript. Arrow functions and their this context. Arrow functions, introduced in ES6, offer a concise syntax for writing functions in JavaScript. Unlike traditional functions, the value of this inside an arrow function is not bound to the function itself. Instead, this retains the value from the enclosing lexical context. Here's how this differs between traditional and arrow functions. In the traditional function, this inside setTimeout does not refer to the function's own this, but to the global object, leading to an undefined name property unless there is a global name. In contrast, the arrow function version captures the this value from the surrounding scope, in this case, the global scope, or the scope where arrow function is defined, making this.name accessible inside setTimeout. This behavior illustrates how this context in arrow functions does not depend on how they are called, unlike traditional functions. Template literals. Template literals are a way in JavaScript to output variables within strings easily. They allow for embedded expressions, multi-line strings, and string formatting using backticks instead of quotes. In this code snippet, we declare two variables, name and age, and use template literals to embed these variables within a string. The backticks allow us to include the variables directly in the string without concatenation, using the syntax variable. This makes the code cleaner and more readable. The output of the console.log will be, "My name is John and I am 30 years old." Default parameters. Default parameters allow functions in JavaScript to be initialized with default values if no value or undefined is passed. This feature simplifies function calls and enhances code readability. In this code snippet, the function greet is defined with a default parameter name, which has a default value of guest. When the function greet is called with the argument Alice, name takes the value Alice. However, when greet is called without any argument, the default value guest is used, which is why hello guest is logged. This behavior demonstrates how default parameters safeguard functions against undefined inputs and provide flexibility in how functions are invoked. REST parameters and spread syntax. REST parameters and spread syntax are powerful features in JavaScript that allow you to work with an indefinite number of arguments as an array and to expand elements of an iterable like arrays in places where multiple elements can be passed. In the sum function, .nums represents a REST parameter that collects all remaining arguments into an array. We use reduce to sum up these values. In the call to sum, .numbers uses spread syntax to expand the numbers array into individual arguments. Therefore, sum.numbers is equivalent to sum 1, 2, 3. This code demonstrates how REST parameters can collect arguments into an array, and how spread syntax can expand an array into individual arguments in a function call. Closures. A closure is a feature in JavaScript where an inner function has access to the outer, enclosing function's variables, a scope chain. This allows for function encapsulation and preservation of state across executions, making it a powerful tool for creating function factories, private data, and function currying, among others. In this example, makeCounter is a function that defines a local variable count and returns another function. This inner function accesses and modifies the count variable, which is lexically scoped within makeCounter. Despite makeCounter's execution context has finished, the count variable remains accessible to the returned function through a closure, allowing it to increment count on each call. This demonstrates how closures can capture and maintain state even after the outer function has returned, making the count variable effectively private and controlled solely through the inner function. Recursion and stack. Recursion occurs when a function calls itself directly or indirectly, allowing for the solution of problems by breaking them down into simpler instances. This concept is often used to solve tasks that can be divided into similar subtasks, like tree traversals, factorial calculation, etc. Understanding how recursion and the call stack work is crucial, as it involves memory allocation for each call and can lead to a stack overflow. Error if the base case is not properly defined or the depth of recursion is too deep. In the given code, the factorial function demonstrates recursion. The function takes one parameter n and multiplies it by the factorial of n-1 until n equals 1, which is the base case. At each function call, a new execution context is pushed onto the call stack, preserving the local variables of each execution context. When the base case is reached, the stack begins to unwind as each context completes and returns its value, ultimately calculating the factorial. This example highlights the key aspects of recursion: a base case to terminate the recursion, recursive calls to the same function with updated arguments, and the use of the call stack to manage the function execution contexts. Immediately invoked function expressions, IIFE. An immediately invoked function expression, IIFE, is a JavaScript function that runs as soon as it is defined. It is a common pattern for encapsulating code and managing local scopes without polluting the global namespace. In the provided code, we define a function directly and invoke it immediately without saving it to a variable. The function creates a local variable message and logs it to the console. Since this function is invoked right after its definition, it is called an F. This approach avoids creating global variables, hence reducing the risk of variable name conflicts and keeping the global scope clean. Function binding. Function binding is a fundamental concept in JavaScript, enabling us to fix the context "this" within a function, regardless of how it is called. This technique is particularly useful when a function needs to be passed around, like a callback, while still retaining its connection to the original object. In this code, we have an object user with a method sayHi that returns a greeting message. When we want to call the sayHi function outside of its containing object, e.g. as a callback function, we need to ensure the function's "this" context points back to the user object. The .bindUser method creates a new function, sayHi, that, when called, has its "this" set to user, regardless of the calling context. Thus, sayHi correctly logs "Hello John," since this.firstName refers to user.firstName. Currying and partials. Currying is a transformative technique of decomposing a function of multiple arguments into a sequence of functions, each with a single argument. It's particularly useful in functional programming for creating a chain of functions where each function takes one argument. Partials, on the other hand, are based on fixing a certain number of arguments for a function, producing another function of smaller arity, number of arguments. Both approaches are powerful in the context of functional programming and help in achieving more modular and expressive code. In the provided code, we define a function curry that takes a function f as an argument. Curry then returns a function that takes an argument a. This function, in turn, returns another function that takes an argument b. Finally, this function calls the original function f with both arguments a and b. We demonstrate this with a sum function that adds two numbers. By currying sum, we're able to call it as curried sum 1, 2, instead of sum 1, 2, demonstrating a chained approach to supplying function arguments. This technique is helpful for creating more versatile and composable functions. The arguments object. In JavaScript, functions have a built-in object called arguments, which allows them to access all the arguments passed to them, regardless of their names or the number of arguments declared in the function definition. This can be particularly useful when creating functions that can handle an unknown number of arguments. The code defines a function, showArguments, that logs the number of arguments passed to it, followed by each argument value. It uses the arguments object to access the argument's length and individual arguments by index. This demonstrates how the arguments object can be used to iterate over all arguments passed to a function, regardless of their number or types. Note, arguments object behaves like an array, but it's not an actual array instance. Hence, array methods cannot directly be called on it unless converted or using methods like array.prototype.forEach.call, arguments, callback. Event loop and call stack. JavaScript operates on a single-threaded event loop, managing the execution of functions using a call stack, a task queue, and an event loop. When a function is called, it's placed on the call stack. If the function performs asynchronous tasks like setTimeout, the callback is queued in the task queue. The event loop checks the call stack. If it's empty, it takes the first event from the queue and pushes it onto the call stack to be executed. In this example, start is logged first, as it's at the top of the call stack. Then the setTimeout function is called, but due to its asynchronous nature, its callback function is moved to the task queue, waiting for the call stack to be empty. End is logged next, since it follows start directly in the synchronous execution flow. Finally, after the call stack is clear, the event loop pushes the callback from setTimeout, which logs setTimeout, off the task queue and onto the call stack, executing it last. Promises, async, await. Promises and async await syntax are at the heart of asynchronous programming in JavaScript. A promise represents a future result of an asynchronous operation, allowing us to handle its success or failure. Async signifies a function always returns a promise, and await is used to wait for the promise to settle, providing a cleaner syntax for promise handling. In the given code, fetchData is an async function that attempts to fetch data from a provided URL. Inside the function, await is used to wait for the fetch request to complete, and then again for the .json method to pass the response body as JSON. If the request or parsing fails, the catch block catches the error, allowing for error handling. This structure provides a much cleaner and more readable approach to dealing with asynchronous operations compared to chaining .then and .catch methods on promises. Error handling with try-catch finally. In JavaScript, error handling is crucial for creating resilient applications. The try-catch finally construct allows us to capture runtime errors, handle them gracefully, and execute cleanup code regardless of the outcome. This structure ensures that the program can recover from unexpected failures and maintain its functionality. In the provided code, risky operation is a function that demonstrates the use of try-catch finally. Inside the try block, we simulate an operation that fails by throwing an error with throw new error, oops. If the error occurs, it's caught by the catch block, which logs the error message to the console. Regardless of whether an error was thrown or not, the finally block executes. This block typically contains cleanup code, ensuring it runs under all circumstances. The flow is: attempt the operation in try, catch any occurring error in catch, and execute finally for cleanup, showing a pattern for robust error handling and resource management. Custom iterable objects. In JavaScript, not only can we work with built-in iterables like arrays or strings, but we can also create our own custom iterable objects. This empowers us to define how the objects should be iterated. For instance, creating a custom iterable can be handy when we have a specific sequence of values we wish to produce during iteration. The example shows a custom iterable object named range, designed to iterate from a start value from to an end value to. The object implements the iterable protocol by including a method keyed by symbol.iterator, which returns an object that conforms to the iterator protocol, having a next method. The next method generates the sequence by returning the current value in an object with done and value properties, and prepares the next value if it's within the range. Once current exceeds 2, next indicates completion by returning done true. Thus, this setup allows for iterating over range with a for.of loop, as if it were a standard iterable. Arrays and their methods. Arrays are foundational data structures in JavaScript, crucial for storing and managing ordered collections of data. They come with a plethora of built-in methods to manipulate these collections efficiently. Understanding these methods is fundamental for effective problem-solving in interviews. In this snippet, we initially declare an array fruits containing 3 elements. The push method adds a new element, date, to the end of the array, expanding its size. Then, the shift method is used, which removes the first element from the array and returns it. Hence, first fruit will be apple. After these operations, the console.log outputs the modified array, which now contains banana, cherry, and date. This example demonstrates how to dynamically adjust the contents of an array using push for addition at the end and shift for removal from the beginning. Stacks and queues. Stacks and queues are fundamental data structures in computer science. A stack is a collection of elements that follows the last in, first out LIFO principle. Imagine a stack of plates. The last plate placed on the stack is the first one to be removed. A queue, on the other hand, follows the first in, first out FIFO principle, similar to people standing in line. The first person in line is the first one to be served. The stack class showcases basic stack operations: push to add an element to the top of the stack, and pop to remove the top element. The underflow condition checks if the stack is empty. Queue class demonstrates queue operations. Enqueue adds an element to the end, and dequeue removes the front element. Similar to stacks, a underflow check ensures the queue isn't empty during a dequeue operation. These classes encapsulate the essence of LIFO and FIFO principles through simple methods, serving as a practical introduction to stacks and queues. Linked lists. A linked list is a linear collection of data elements where each element points to the next. It's a dynamic data structure, which means it can grow or shrink in size. They are efficient for insertion and deletion operations. In the provided code, we define a class for a node in the linked list containing data and a pointer to the next node. Then, we define a linked list class with a method to add new nodes. Initially, the list is empty, head is null. The add method inserts a new node at the end. If the list is empty, the new node becomes the head. Otherwise, we traverse the list until we reach the last node, then link the new node to the end of the list. Trees, binary search trees, tree traversal algorithms. Trees are nonlinear data structures composed of nodes connected by edges, forming a hierarchical structure. A binary tree is a tree where each node has at most 2 children. When these children are ordered, such that for any given node, all elements in the left subtree are less than the node, and all elements in the right subtree are greater, it's called a binary search tree, BST. Tree traversal algorithms are methods for visiting all the nodes in a tree, generally classified into breadth-first search, BFS, and depth-first search, DFS types, including in-order, pre-order, and post-order traversals. The code snippet defines a class tree node representing each node in a binary tree, with value, left, and right properties. It also includes an in-order traversal function, demonstrating a DFS tree traversal algorithm. In an in-order traversal, the algorithm recursively visits the left subtree, processes the current node, e.g., prints the node's value, and then recursively visits the right subtree. This traversal method ensures nodes are visited in their non-decreasing order, which is particularly useful in binary search trees, BSTs, where this property is maintained by the structure of the tree itself. Graphs, representation, traversal. A graph is a collection of nodes, also known as vertices, connected by edges. Graphs can be used to model various real-world systems like social networks or the internet. Graphs can be represented in various ways, such as adjacency matrices or adjacency lists. Traversal is the process of visiting each node in the graph. There are 2 primary methods for graph traversal: depth-first search, DFS, and breadth-first search, BFS. In the provided code, we define a simple graph class to represent a graph using an adjacency list. The graph class has methods to add vertices, add vertex, and edges, add edge. Each vertex is stored as a key in this.adjacency list, with its value being an array of its adjacent vertices. This representation allows for efficient lookup of a vertex's neighbors, crucial for traversing the graph. Adding edges is undirected in this snippet, meaning if we add an edge from vertex 1 to vertex 2, we automatically add an edge from vertex 2 to vertex 1, indicating a bidirectional connection. Sorting algorithms: bubble, selection, insertion, merge, quick, heap. Bubble sort is a simple comparison-based sorting algorithm. It repeatedly steps through the list, compares adjacent elements, and swaps them if they are in the wrong order. The pass through the list is repeated until the list is sorted. This bubble sort function iterates through the array multiple times with a nested loop. For each outer loop iteration, it compares each pair of adjacent items and swaps them if they're in the wrong order, effectively bubbling the highest unsorted value to its correct position. As each iteration of the outer loop completes, the range of the inner loop decreases because the elements at the end of the array are already sorted. Searching algorithms: linear, binary, jump, interpolation. Linear search is the simplest searching algorithm that scans one item at a time, from the beginning of the list until the desired element is found or the list ends. The code defines a function, linear search, that takes an array R and a value X to be searched within the array. Using a for loop, it iterates over each element in the array, comparing each element with X. If a match is found, it returns the index of the element. If the loop completes without finding the element, it returns -1, indicating that the element was not found in the array. Hash tables. Hash tables, also known as hash maps, are a type of data structure that provides a way to map keys to values. This allows for efficient data retrieval and storage. A hash function is used to compute an index into an array of slots from which the desired value can be found. Our code outlines a basic hash table class, including a constructor, a hash function score hash, and methods to set and get key value pairs. The constructor initializes an array to store data. The hash method generates a pseudo-random index based on the key to determine where to store the value in the array. The set method uses the hash function to find where to store the key value pair in the array, dealing with potential collisions by storing values at the same index in a nested array. The get method retrieves a value by its key, searching through the nested array at the calculated index if necessary. Set operations. In JavaScript, a set is a collection of unique values. Set operations such as union, intersection, and difference are crucial for various computing tasks. These operations allow us to combine, compare, and contrast different sets of data efficiently. Understanding how to implement these using JavaScript's set object is essential for solving complex problems. The code demonstrates how to perform union, intersection, and difference operations on two sets in JavaScript. For the union operation, we combine elements of both sets, ensuring unique values using the set constructor. The intersection operation uses the filter method to select only the elements present in both sets by checking if set B contains each element of set A. Lastly, the difference operation finds elements in set A that are not in set B, again using filter to select elements and has method to check existence in the other set. These operations illustrate how set theory concepts can be practically applied in programming to manipulate collections of data. Dynamic programming. Dynamic programming, DP, is a technique in computer science to solve problems by breaking them down into simpler subproblems, solving each subproblem just once, and storing their solutions. It is particularly useful for optimization problems. By storing the results of expensive function calls and reusing them when the same inputs occur again, DP ensures that each problem is only solved once, thus reducing the computation time. Let's consider the Fibonacci sequence, a classic example to demonstrate DP. In this code snippet, we implement a function to calculate the nth Fibonacci number using dynamic programming. The Fibonacci sequence is defined such that each number is the sum of the two preceding ones. We initialize an array DP with the first two Fibonacci numbers, 0 and 1. We iterate from 2 up to n and fill the DP array with the sum of the two immediately preceding numbers. This way, we avoid recalculating the Fibonacci numbers for smaller values, leading to a significant efficiency gain. The approach is both time efficient, with a complexity of O(n), and space efficient, considering it only stores the sequence up to n rather than all calculated values. Prototypal inheritance. Prototypal inheritance is a feature in JavaScript that allows one object to inherit the properties and methods of another. It's a fundamental part of JavaScript's prototype-based inheritance system, where objects can have a prototype from which they can inherit features. In the provided code, a parent function constructor is defined with a property. A method is added to parent's prototype that returns the value of the parent property. A child function constructor is also defined, which has its own property. Child's prototype is set to an instance of parent, enabling child instances to access parent's properties and methods through prototypal inheritance. This is shown when child instance is able to call both getParentValue and getChildValue, demonstrating that child has successfully inherited from parent. This pattern is commonly used to simulate class-like inheritance in JavaScript. Constructor functions. Constructor functions are a foundation of object-oriented programming in JavaScript, allowing us to create objects of the same type effectively. Similar to a blueprint, A constructor function outlines the structure and behaviors, methods that objects created from it will inherit. The car function is a constructor that initializes objects with properties make, model, and year based on the arguments passed during instantiation, new car. The displayCarInfo method is also defined within the constructor, allowing each instantiated object to use this method to print its details. Using this within the constructor refers to the new object being created. The new keyword is crucial. It creates a new instance of car, setting this within the constructor to point to the newly created object, allowing the properties and methods defined in car to be accessed through myCar. ES6 classes. ES6 classes provide a much clearer and more concise syntax to create objects and deal with inheritance. This feature is a syntactical sugar over the existing prototype-based inheritance and doesn't introduce a new inheritance model in JavaScript. It simplifies the way we create objects and manage inheritance. The class keyword introduces a new class animal. A class is a template for creating objects. It encapsulates data for the object. The constructor method is a special method for creating and initializing objects created with a class. The dog class extends the animal class, inheriting its properties and methods, and we override the speak method to reflect a dog's sound. The super keyword is used to call the constructor of the parent class and pass the name parameter to it. Finally, we create an instance of the dog class named Rex and call its speak method, demonstrating polymorphism, the ability of a subclass to redefine methods of its superclass. Private and public class fields. In JavaScript, class fields can be categorized into two main types, public and private. Public fields can be accessed from any part of the program, while private fields are only accessible within the class they are declared. JavaScript denotes private fields with a shack prefix. In the example, car class has a private field mileage that stores the mileage of the car. It is initialized in the constructor. The getMileage method is public and provides read access to the private mileage. Attempting to directly access mileage outside the car class results in a syntax error, demonstrating the encapsulation provided by private fields in enforcing class invariance. Mixins. Mixins are a tool in JavaScript for creating classes that combine behaviors from multiple sources, effectively allowing for the composition of classes. Instead of traditional inheritance, where a class extends another class, mixins allow an object or class to incorporate properties and methods from multiple sources. This can promote code reusability and avoid some problems associated with inheritance. This example showcases the basic idea of mixins in JavaScript. The sayMixin object defines a method say that logs a given phrase to the console. The sayHiMixin uses inheritance, proto, to inherit from sayMixin and adds two methods, sayHi and sayBy, both utilizing the say method. The object assign method is then used to mix sayHiMixin into user class's prototype, effectively adding sayHi and sayBy methods to any user instance. This illustrates how mixins allow for the distribution of methods across classes without requiring a direct inheritance chain. Polymorphism. Polymorphism in JavaScript allows objects of different classes to be treated as objects of a common superclass. It's a core concept in OOP that enables a single interface to represent different underlying forms, data types. In JavaScript, polymorphism is often achieved through prototypes or class-based syntax, starting from ES6. This allows for methods to act differently based on the object it is called upon. Let's explore how polymorphism works with a simple example involving animals speaking. In the example, animal is a superclass with a method speak. Both dog and cat classes inherit from animal, but override the speak method to return their specific sounds. This demonstrates polymorphism. Despite dog and cat being instances of their respective classes, they're treated as animal objects when it comes to calling the speak method. The method behaves differently based on the object's actual class, which is the essence of polymorphism. This concept enables flexible and scalable code design, where one interface can interact with objects from different classes seamlessly. Encapsulation. Encapsulation is a fundamental concept in object-oriented programming, OOP, that restricts direct access to an object's data and methods from outside the object itself. It helps in bundling the data, properties, and methods that operate on the data into a single unit, called an object, and restricts access to some of the object's components. This is usually done using access modifiers like private, protected, or public, which can control the visibility of a class's properties and methods. In JavaScript, we achieve encapsulation through closures and the usage of get and set methods to control access to object properties. In this code, we define a person class encapsulating the properties name and age by using JavaScript functionalities instead of traditional access modifiers. The properties name and age are defined using let within the constructor, making them private to the instance Bob, and cannot be directly accessed from outside the class. The class provides public methods getName, getAge, and setAge to read and modify these properties, demonstrating encapsulation. This way, we're controlling access to the internal state of the person object, ensuring data integrity and abstraction. Composition versus inheritance. In the design of software, especially when using object-oriented programming, OOP, developers must choose between composition and inheritance to establish relationships between objects. Inheritance is a mechanism for defining a new class child from an existing class parent, thereby inheriting fields and methods. Composition, on the other hand, involves building more complex objects by combining simpler ones, indicating a has-a relationship rather than an is-a relationship as seen with inheritance. In the code, the rectangle class is defined with properties for width and height, and a method to calculate the area. The square class demonstrates inheritance by extending rectangle and using super to pass the side length as both width and height, making use of the rectangle's functionality to compute the area. On the other hand, the colored rectangle class shows composition by holding a rectangle instance, not extending it, and a color property. This approach illustrates a has-a relationship, indicating that a colored rectangle has a rectangle and a color, but it is not a type of rectangle. This method of composition over inheritance is favored for its flexibility and ease of maintenance, especially in complex systems where relationships can change over time. Callback functions. Callback functions are the foundational concept in JavaScript for handling asynchronous operations. They are functions passed into another function as an argument, which is then invoked inside the outer function to complete some kind of routine or action. In this example, process user input takes a callback function as an argument, here greeting. When called, process user input asks the user for their name via a prompt, then passes this name to the greeting function by invoking it, callback name. This effectively demonstrates how a callback function can be used to defer execution of a code block until a certain task, in this case, getting user input, is completed. Promises. A promise in JavaScript is an object that represents the eventual completion or failure of an asynchronous operation. It allows you to write asynchronous code in a more synchronous fashion by using .then, .catch, and .finally methods. In the code, we create a function isEvenNumber that returns a promise. The function takes a number and checks if it's even or odd. If the number is even, the promise is resolved with the message even number. If odd, it's rejected with odd number. We use .then to handle the resolved case, logging the success message. .catch is used to handle the rejected case, logging the error message. This demonstrates how promises help manage asynchronous operations by allowing you to chain operations and manage errors. Async and await. In modern JavaScript, the async await syntax offers a cleaner and more readable way to work with asynchronous code compared to callbacks and promises. Marking a function with the async keyword indicates that the function returns a promise, and the await keyword can be used inside async functions to pause the execution until the promise is resolved. In this code, fetchData is an async function that tries to fetch data from a URL using the fetch API. The await keyword pauses the execution inside fetchData until fetch resolves with a response. Then it pauses again until the response.json promise resolves with the actual data. If the promises reject, the error is caught and logged by the catch block. This pattern allows handling asynchronous operations in a synchronous-like manner, greatly improving readability and error handling. Promise.all, promise.race. Promise.all is used when you want to run multiple promises in parallel and wait for all of them to resolve. It takes an array of promises and returns a single promise that resolves when all of the promises in the array have resolved, or when the array contains no promises. It rejects immediately upon any of the past promises, rejecting. In the code, promise.all is passed two promises that resolve with the strings hello and world. When both promises resolve, promise.all also resolves, returning an array of the results, hello world. This array is then joined into a single string, hello world, and logged to the console. If any promise had rejected, the catch block would execute, logging the error. Handling multiple asynchronous operations. Dealing with multiple asynchronous operations can be challenging, but is crucial in web development to enhance user experience. JavaScript provides elegant solutions like promises, async await, and promise.all to handle this elegantly. In the provided code, fetch data is a function that simulates fetching data asynchronously and returns a promise. The handle operations function demonstrates handling multiple asynchronous operations using async await. It awaits the resolution of fetch data twice, effectively pausing execution at each await until the promise resolves, then logs the results. This approach ensures that operations are handled in a predictable manner, even though each operation is asynchronous. It's a simplistic way to illustrate the handling of multiple asynchronous operations in a sequence, providing an intuitive and cleaner code structure for dealing with asynchronous JavaScript. Using async await with loops. Understanding how to use async await within loops is crucial for handling asynchronous operations in an ordered manner, especially when dealing with a sequence of promises. This technique is often required when you have to perform API calls or database operations for a list of items one after the other, or even in parallel, but with a controlled flow. In the provided code snippet, processArray is an async function that takes an array as an argument. Within this function, we're using a for.of loop to iterate over each item of the array. The key part here is the await keyword before doSomethingAsync item. This ensures that the function waits for the promise returned by doSomethingAsync item to be resolved or rejected before moving on to the next iteration. By doing so, we are able to maintain a synchronous flow of execution for asynchronous operations, which is particularly useful when the order of operations matters, such as when the result of one operation depends on the completion of the previous one. Dealing with asynchronous errors. Handling errors in asynchronous JavaScript is critical for writing robust applications. Asynchronous operations, such as promises and async await, require specific patterns to catch and handle errors effectively. This ensures your app can gracefully respond to issues without crashing or hanging. The provided code demonstrates error handling in an asynchronous function using async await syntax. The try block attempts to fetch data from a URL. If the fetch operation fails, i.e., the promise is rejected or the response is not OK, an error is thrown. The catch block catches these errors, allowing the developer to handle them gracefully, here by logging the error to the console. This pattern ensures the application remains stable even if the data fetch fails. Web workers. Web workers provide a simple means for web content to run scripts in background threads. Since JavaScript runs in a single thread, performing heavy tasks can freeze or slow down the UI. Workers allow these tasks to be performed without interrupting the user experience by running them in a separate thread. This code checks if the browser supports web workers. If it does, it creates a new worker from a worker.js file. The post-message method is used to send data to the worker. In the worker, data can be processed, and the result is sent back to the main thread through the onMessage event listener. The example demonstrates how to set up and communicate with a web worker, initiating communication from the main script with post-message and handling received messages from the worker. It effectively showcases the capability to perform tasks in the background without affecting the user interface responsiveness. Service workers. Service workers act as a proxy between the web application and the network, enabling the creation of effective offline experiences, background syncs, and push notifications. They are JavaScript workers that can intercept and cache network requests, helping improve the performance and providing offline capabilities to web applications. This code snippet demonstrates how to register a service worker in a web application. Firstly, it checks if the browser supports service workers. Upon the Windows load event, it attempts to register a service worker script located at /serviceworker.js. If the registration is successful, it logs a success message with the scope of the registration. In case of failure, an error message is logged. The scope of the service worker determines from which path the service worker controls requests. Pure functions. In functional programming, pure functions are essential. These functions ensure predictability and reliability in code. A pure function consistently returns the same result given the same arguments, and it does not cause any observable side effects. In the provided example, calculate area is a pure function. It calculates the area of a circle given its radius. This function adheres to two main criteria of pure functions. 1. Given the same radius, it always returns the same result, ensuring it's deterministic. 2. It does not interact with or modify external state, no I/O operations, global variable manipulations, etc., thus avoiding side effects. These characteristics make calculate area predictable and easy to test. Function composition. Function composition is a powerful concept in functional programming that allows you to combine multiple functions into a single function. The result of each function is passed as the argument to the next. This helps in creating readable, maintainable, and declarative code by building complex operations out of simpler functions. In this example, we define a generic compose function that takes two functions f and g as arguments and returns a new function. This new function, when called with an argument x, first applies g to x, then applies f to the result of gx. We also define two simple functions, toUpperCase, which converts a string to uppercase, and exclaim, which adds an exclamation mark to a string. Finally, we compose exclaim and toUpperCase into a new function shout. When shout hello is executed, it first converts hello to uppercase, then adds an exclamation mark, outputting hello. This demonstrates how function composition can create a more complex function by combining simple ones. Higher-order functions. Higher-order functions are a core concept in JavaScript and functional programming. They are functions that can take other functions as arguments or return a function. This allows for flexible and reusable code. In the provided code, we define two simple functions, greet and farewell, each taking a name and returning a greeting string. The function createGreeting is a higher-order function because it takes another function, greeting function, and a name as arguments. It then calls the provided greeting function with the name and returns the result. This design showcases the power of higher-order functions, allowing for flexible execution of different functions. Lazy evaluation. Lazy evaluation, or call by need, is a strategy that delays the evaluation of an expression until its value is needed. It can improve performance by avoiding unnecessary calculations, and also allows for the definition of potentially infinite data structures. Let's examine how lazy evaluation can be implemented in JavaScript using generators, which are functions that can be paused and resumed, and are well suited for implementing lazy behaviors. The Fibonacci generator function demonstrates lazy evaluation. The Fibonacci sequence is potentially infinite, but calculating its values on demand allows us to use it efficiently. This is achieved by generating values only when next is called on the fib sequence iterator. Each call to next resumes the function until it hits the next yield, where it pauses and returns the current value. This mechanism illustrates the principle of lazy evaluation. The function computes its resulted values only as needed, rather than pre-computing a potentially infinite sequence up front. Monads. Monads in JavaScript can be understood as design patterns used to handle side effects, manage asynchronous operations, and work with pure function pipelines, ensuring errors do not break the application flow. A common monad example is the promise, which encapsulates asynchronous operations and their potential failures into manageable units. In the code, we define a maybe monad, which helps manage null and undefined values in a program. The maybe function returns an object with two methods, bind and value of. Bind takes a function and applies it to its value if it's not null or undefined. Otherwise, it returns a maybe of null. This prevents errors when chaining operations on possibly null values. The +1 function is an example of a simple operation that can be performed on a value inside a maybe monad. Finally, value of is used to extract the final result after operations are applied. Functors. In JavaScript, functors are objects that can be mapped over, similar to arrays. They are structures that implement a map method, allowing transformations without changing their structure. Essentially, a functor is any data type that supports a map operation. Let's explore this concept with an example. In this code, we have an array of numbers, which acts as our functor since arrays in JavaScript inherently support the map operation. The +1 function is applied to each element in the array through the map method, resulting in a new array where each original value is incremented by 1. This demonstrates the functor property of being able to be mapped over, applying a function to each of its values, without altering the original data structure. Immutability. Immutability, a core concept of functional programming, dictates that data cannot be modified after it's created. Instead of changing the original data, operations should create and return new data based on the originals. This approach helps prevent side effects and makes the state of the program more predictable, improving reliability and readability. In this example, original array is an array of numbers. Instead of modifying original array directly, we use .map to create a new array, where each item is doubled. Original array remains unchanged, demonstrating immutability. This pattern avoids side effects caused by changing the original data and makes it easier to understand how data flows through the application. Side effects and state management. In functional programming, managing state and side effects is crucial for maintaining code purity and predictability. Side effects are operations that alter the program's state or interact with the outside world, such as modifying a variable, logging to the console, or making an HTTP request. Pure functions, in contrast, depend only on their inputs and produce the same output for the same inputs without causing side effects. Below is an example demonstrating a simple case of managing side effects in a function. In the example, increment state modifies a global variable state, hence it introduces a side effect, making it an impure function. Every call to increment state changes the global state, affecting the entire program's behavior unpredictably. On the other hand, pure increment is a pure function as it depends only on its input, n, and always returns the same output for the same input without altering any external state. Managing state without side effects, as seen in pure increment, promotes a more predictable, testable, and maintainable codebase in functional programming. Currying. Currying is a process of converting a function that takes multiple arguments into a sequence of functions, each taking a single argument. This technique allows for partial application of function arguments, enabling the creation of simpler, reusable functions. Let's dive into an example to clarify this concept. In this example, we start with a simple multiply function. Using the curry function, we transform multiply into curried multiply, which takes one argument at a time. We then create multiply by 2, a new function that permanently fixes the first argument of multiply to 2. Now, when multiply by 2 is called with an argument 3, it completes the multiply operation by using both arguments. This illustrates how currying can simplify functions and make them more versatile in functional programming. Memoization. Memoization is an optimization technique used to speed up function execution by storing the results of expensive function calls and returning the cached result when the same inputs occur again. It's particularly useful in optimizing functions that perform heavy computations. In this code, memoize is a higher-order function that takes a function fn as an argument and returns a new function. This new function checks if the result of calling fn with a given set of arguments is already in cache. If so, it returns the cached result, avoiding the need to re-execute fn. If not, it executes fn, caches the result for future invocations with the same arguments, and returns the result. The key for caching is generated by serializing the arguments array, ensuring uniqueness for function calls with different arguments. This implementation of memoization optimizes recursive computation of the factorial by caching previous results, significantly reducing the computational cost for repeated calls. Reflow and repaint in the DOM. Understanding the concepts of reflow and repaint is crucial for optimizing web app performance. Reflow occurs when changes are made to element sizes, positions, or contents, leading the browser to recalculate element positions. Repaint happens when changes affect the visibility or colors of elements without affecting their layout. Both processes can degrade performance if triggered excessively. In this example, changing the color of my element triggers a repaint because it does not alter the layout. However, changing its width causes a reflow, as the browser must recalculate the layout of my element and potentially other affected elements. Minimizing unnecessary DOM manipulations and batch reading or writing styles can help reduce reflow and repaint costs, thus improving performance. Web workers and performance. Web workers in JavaScript allow you to run scripts in background threads, separate from the main execution thread of a web application. This enables intensive tasks not to block the UI, enhancing performance, especially in scenarios where heavy computation is involved. This example checks if the browser supports web workers and, if so, creates a new worker object while pointing to an external script, worker.js. It then sends a message to the worker thread using post-message and sets up an on-message handler to receive messages from the worker. If the browser doesn't support web workers, it logs an error message. This demonstrates how to offload tasks to a background thread, allowing the main thread to stay responsive. Lazy loading of resources. In modern web development, optimizing the loading time and performance of a website or application is crucial. One effective technique is lazy loading, a strategy that delays the loading of non-critical resources at page load time. Instead, these resources are loaded at the moment of need, which can significantly improve performance, especially in cases with heavy content like images or scripts. The code snippet is an example of lazy loading images using plain JavaScript. When the page's DOM is fully loaded, DOM content loaded, it finds all images with a data lazy SAR attribute. This attribute holds the actual image URL that should be loaded lazily. For each such image, it sets the SARC attribute to the value of data lazy, initiating the image load. As soon as the image is loaded, img.onload, the data lazy SARC attribute is removed. This technique ensures images are loaded only when needed, improving page load time and reducing unnecessary bandwidth usage. Debouncing and throttling. Debouncing in JavaScript is a practice used to improve browser performance by limiting the rate at which a function can fire. A debounced function will only be called after a certain amount of time has elapsed since the last time the debounced function was invoked. This is particularly useful for events that trigger frequently, such as resizing, scrolling, or key pressing. The debounce function takes a function func and delay as arguments. It returns a new function that, when called, clears any previous timer and sets a new timeout. If the returned function is invoked again before the delay has elapsed, the previous timeout is cleared and a new one is set, effectively restarting the delay. When the delay finally elapses without any new invocations, the original function func is called with the provided arguments. This ensures that func is only called after a period of inactivity of delay milliseconds. Optimizing JavaScript execution. Optimizing JavaScript execution is crucial for improving the performance of web applications. It involves using efficient algorithms, minimizing reflows and repaints, and leveraging browser capabilities. Here, we focus on avoiding unnecessary calculations inside loops, a common performance bottleneck. In the given code snippet, expensive function is called in each iteration of the loop, even though its result may not change frequently. Moving it outside the loop can significantly improve performance, especially for large datasets. This demonstrates a common optimization technique, reducing the computational cost in repetitive operations. Always assess the necessity of computations within loops and, if possible, pre-calculate values or conditions. Memory management and garbage collection. In JavaScript, memory management is handled automatically via a process called garbage collection. This process seeks to reclaim memory allocated by objects that are no longer in use by the program, hence unavailable for future allocations. Understanding how this works helps developers write more efficient and performant code by minimizing memory leaks and inefficient memory usage. In this snippet, an object is created and assigned to the variable customer. Initially, the memory is allocated for this object. When we set customer to null, there are no more references to the object, making it unreachable. Unreachable objects are considered for garbage collection, meaning the JavaScript engine can free up the memory once allocated to them. This is a fundamental aspect of memory management in JavaScript, enabling efficient use of resources by automatically cleaning up memory that's no longer needed. Avoiding memory leaks. Memory leaks in JavaScript occur when unused memory is not properly released back to the system, leading to increased resource consumption and potential application crashes. A common source of leaks is when large data structures or event listeners are not properly disposed of. The example below illustrates how to avoid memory leaks by properly managing event listeners. In this code, we create a button event listener in a way that allows us to avoid a memory leak. First, we define a setup function, setUpClickListener, that attaches a click event listener to a button. Importantly, this function returns another function, cleanup, designed to remove the event listener. When the button is no longer needed, or the component it belongs to is about to be unmounted, we call this cleanup function. This manual detachment of the listener ensures that references to the DOM element and the handler function are released, allowing the JavaScript garbage collector to reclaim the memory, thus preventing a potential memory leak. WebAssembly. WebAssembly, often abbreviated as WASM, is a binary instruction format for a stack-based virtual machine. It's designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. WASM is designed to be fast, efficient, and safe to execute, making it an ideal technology for high-performance tasks that JavaScript might struggle with. It works alongside JavaScript, allowing you to write performance-critical sections in languages like C, C++, Rust, etc., and compile them into WASM to run in the browser. This code snippet demonstrates loading a WebAssembly.wasm module using JavaScript. The WebAssembly.instantiateStreaming method efficiently compiles and instantiates a WebAssembly module directly from a binary stream, which is fetched from the server, module.wasm in this case. The import object argument can be used to provide an object containing imports required by the module, such as functions or values from JavaScript. Once the promise resolves, the result object contains an instance of the WebAssembly module, which now can be interacted with, allowing the WASM compiled functions to be executed. This integration allows high-performance code to run in the web environment, supplementing JavaScript's capabilities. Using performance profiling tools. Performance profiling tools are essential for understanding the runtime behavior of your application and identifying bottlenecks. Modern web browsers include built-in tools like Chrome's Performance tab that can capture and analyze the runtime performance of your JavaScript code. This simple code snippet demonstrates how to use console.time and console.timeEnd to measure the execution time of a function in JavaScript. This is a basic yet powerful way to quickly assess the performance of code snippets during development. For more detailed analysis, users should resort to browsers' profiling tools, where they can record sessions and inspect the call stack, memory usage, and other important metrics. Document Object Model, DOM. The Document Object Model is a programming interface provided by the browser, allowing scripts to dynamically access and update the content, structure, and style of a document. Through DOM, web pages can be scripted to create dynamic content. Here's a simple example demonstrating how to manipulate DOM elements. In this code, document.getElementById selects the HTML element with the ID demo. The .innerHTML property is then used to modify the content of this element. By setting it to Hello DOM, we dynamically change the text inside the element with ID demo to display Hello DOM. This shows how the DOM can be used to interact with and modify HTML elements directly from JavaScript. Browser Object Model, BOM. The Browser Object Model provides JavaScript access to browser-specific objects. It allows JS to interact with the browser, enabling functionalities like browser navigation, manipulating browser window properties, and working with the user's screen details. Unlike the Document Object Model, which deals with the document's content, BOM handles browser components outside the document content. This code manipulates the BOM to change the current browser window's location to h/double.example.com. The window object is a part of BOM and represents the browser window. It hosts a variety of functions and objects. In this case, we use its location object, which represents the URL of the web page. Setting the href property of location to a different URL instructs the browser to navigate to that URL. Thus, JavaScript, through BOM, changes the current web page. Events and event handling. Events in JavaScript are actions or occurrences that happen in the system you're programming, which the system tells you about, so you can respond to them in some way if desired. Event handling is the mechanism by which we can program our web page to react to these events. In the code above, document.getElementById (btn) targets an HTML element with the ID btn. The addEventListener method is used to attach an event handler to the element. The first argument click specifies the type of event to listen for. The second argument is a function, which is the action to be taken when the event occurs. Here, when the button is clicked, an alert box pops up with the message, "Button clicked." This is a fundamental pattern for event handling in JavaScript, enabling interactive web pages. Forms and validation. Forms are the backbone of user interaction on web pages. Validation is the process of ensuring that the user inputs data in the expected format. JavaScript plays a crucial role in client-side validation, enhancing the user experience by providing immediate feedback. Let's consider a simple example of form validation, where we ensure that the user enters an email in the correct format. This code snippet showcases a fundamental way to perform client-side validation using JavaScript. First, we select the form element. Then, we listen for the submit event. Before proceeding to submit the form, we check if the email address entered matches a simple regular expression, regex pattern, that validates email format, i.e., something@something.something. If the input does not match the regex, we display an alert to the user indicating the error, and prevent the form from being submitted with event.preventDefault. This prevents sending the form data until the user corrects the input, enhancing the form's integrity without requiring a round trip to the server. Cookies, web storage, local storage, session storage. Web storage allows web applications to store data locally within the user's browser. Unlike cookies, web storage is more secure, and larger amounts of data can be stored locally without affecting website performance. We'll cover two main types, local storage and session storage. In the code snippet, local storage is used to store data with no expiration time. When we set an item using local storage.setItem user John Doe, it saves a user with the name John Doe. This data stays in the browser until explicitly deleted. We retrieve this data using local storage.getItem user. Session storage is similar but limited to a session's lifetime. The data stored using session storage.setItem session data session value is only available while the page session lasts. Closing the tab or browser would clear this data. We access session storage data with session storage.getItem session data. This shows how both storage types can be utilized in web applications for persistent and session-based data storage. Session management. In web development, session management is crucial for maintaining user data across multiple requests. It enables web applications to store and retrieve user-specific information, like login status, across different pages. JavaScript, particularly on the client side, interacts with session management using Web Storage API, local storage, and session storage. We'll explore how to use session storage for session management. This code snippet demonstrates basic session management using session storage. Initially, it checks if a user data exists in the session storage. If it does, it retrieves and logs the username. If not, it sets the user data to John Doe and logs a message indicating a new user session. Session storage is suitable for temporary data that should only persist for the duration of the page session. It is cleared once the tab is closed, making it different from local storage, which persists data across sessions until explicitly cleared. Cross-origin resource sharing, CORS. CORS is a security feature that restricts web applications from making requests to a domain different from the one which served the first page. This is implemented to enhance web applications' security by preventing malicious websites from reading sensitive data from other sites. However, when you need to make legal cross-origin requests, the server must include specific headers to allow it. This header example is set on the response from the server to indicate that the resource can be shared with any domain, acts as a wildcard. While this solves accessibility issues, using a wildcard can expose the resource to attacks from any website. Therefore, it's recommended to specify only trusted domains rather than using a wildcard for production applications. For instance, setting access control allow origin https:/trusteddomain.com would restrict access to requests originating only from /trusteddomain.com. WebSockets. WebSockets provide a way for browsers and servers to communicate in a bidirectional, full duplex manner over a single long-lived connection. This is useful for real-time applications like chat apps, live sports updates, or multiplayer online games. The code snippet creates a new WebSocket object, connecting to ws/www.example.com. Upon successfully establishing a connection, on open event, it sends a message to the server, "Hello server." When the server sends back a message, the onMessage event triggers, logging the server's message. Additionally, onRaw and onClose events are set up to handle errors and the closing of the connection, respectively. This is a basic setup for communicating with a server via WebSockets. Fetch API, XML HTTP request. The Fetch API and XML HTTP request are two popular ways to make HTTP requests in JavaScript, allowing web pages to asynchronously load data and resources. While the Fetch API is a modern, promise-based API, providing a more powerful and flexible feature set, XML HTTP request is an older API but still widely used for compatibility reasons. The code snippet demonstrates how to make a GET request to api.example.com/data using the Fetch API. First, fetch is called with the URL, returning a promise that resolves to the response to that request. The .then method is used to handle the response, converting it to JSON with response.json. This returns another promise that resolves with the result of passing the body text as JSON. Finally, the passed data is logged to the console. If any error occurs during the fetch, the catch method catches it, logging an error message. Cross-site scripting, XSS. Cross-site scripting, XSS, is a vulnerability that allows attackers to inject malicious scripts into web pages viewed by other users. This can lead to data theft, session hijacking, and other security breaches. Prevention involves sanitizing and validating user inputs. In this code snippet, we're sanitizing the user input to prevent XSS attacks. We use the replace method on the user's input, user input, to remove any occurrences of script, tags, and their contents. This is a rudimentary way to prevent simple XSS attacks by ensuring that any script tags entered by the user are stripped out before being rendered on the page. However, in a real-world scenario, it's advisable to use libraries designed for input sanitization, as they cover a broader range of XSS attack patterns and offer more security. Cross-site request forgery, CSRF. Cross-site request forgery, CF, is an attack that forces an end user to execute unwanted actions on a web application in which they're currently authenticated. Attackers can compromise user requests to perform unwanted actions by leveraging the user's authentication cookies. To protect against CSRF, websites implement a token-based defense mechanism. In the code, a middleware function, checkCSRF is defined to validate CSRF tokens for post requests. When a post request is made, it retrieves the CSRF token sent by the client in the header xCSRF token and compares it with the tokens stored in the user's session. If the tokens don't match, it returns a 403 error, indicating a CSRF token mismatch. This prevents CSRF attacks by ensuring that every post request originates from the trusted client with a valid session. Content Security Policy, CSP. Content Security Policy, CSP, is a security standard introduced to prevent XSS, cross-site scripting attacks, by restricting where resources can be loaded from. It allows web developers to declare a whitelist of trusted content sources, thus offering control over the content that browsers are allowed to load on their web pages. The code snippet is an example of a CSP header that a website might use. Default-sarc self restricts all content sources to the same origin as the document itself, except for images, imgsarc, which can be loaded from anywhere over HTTPS. It also specifies that no child browsing contexts, like iframes or frames, are allowed. Child-sarc none. This CSP header effectively reduces the risk of XSS attacks by limiting the types of content that can be included in the web page. Same origin policy. Same origin policy, SOP, is a critical security concept in web development that restricts how a document or script from one origin can interact with resources from another origin. An origin is defined by the scheme, protocol, host domain, and port of a URL. This policy helps to prevent malicious attacks, such as cross-site scripting, XSS, and cross-site request forgery, CSRF, by ensuring that scripts run only within the same origin or are explicitly allowed to access resources from another origin. The code snippet checks if the origin of the script being executed, window.location.origin, is the same as the origin of the document it's trying to access, document.location.origin. If they are not the same, it triggers an alert indicating a cross-origin script detection. This simple check is a practical application of the same origin policy to alert on potential cross-origin interactions that might not be authorized, helping to mitigate potential security vulnerabilities. HTTPS and TLS. HTTPS, Hypertext Transfer Protocol Secure, and TLS, Transport Layer Security, are foundational technologies for secure communication over the Internet. HTTPS incorporates TLS to encrypt HTTP requests and responses, ensuring data integrity and privacy. This example code demonstrates a basic use of the HTTPS module in Node.js to make a GET request to https://example.com. The request is made over HTTPS, utilizing TLS encryption automatically. When data is received from the server, it is pieced together until the full response is received. Finally, any errors that occur during the request are logged. This showcases how HTTPS and TLS protect data integrity and confidentiality in web communications by encrypting the data transmitted between the client and server. Password hashing. Password hashing is a critical aspect of modern web security, ensuring user passwords are stored securely. Rather than storing plain text passwords, which are susceptible to breaches, hashing transforms them into a fixed-size string of characters, a process that is irreversible. Here, we'll use the bcrypt library in Node.js to hash and compare passwords. In the code snippet above, we use the bcrypt library to hash a plaintext password with a salt, enhancing security by adding randomness. bcrypt.hash is used to generate the hash, taking the password and salt rounds, the cost factor determining how much computing power is needed to calculate the hash, as parameters. After hashing, the password is stored in the database in its hashed form, not plaintext. Then, to authenticate a user, bcrypt.compare is used, which compares a submitted password to the stored hash. If they match, result is true, indicating successful authentication. This process ensures passwords are never stored or transmitted in a form that can be easily compromised. Web security headers. Web security headers are crucial for protecting a website from various attacks and ensuring the privacy of its users. By setting specific HTTP headers, developers can control the behavior of web browsers to enhance security. Here, we'll explore some common security headers. The code demonstrates how to set several important security headers in an Express.js application. Content security policy restricts resources, such as scripts or styles, the browser is allowed to load, enhancing protection against cross-site scripting attacks by specifying that only resources from the same origin, self, should be loaded. Xframe options, set to deny, prevents clickjacking attacks by disallowing the site to be framed by other pages. Xcontent type options, with value no-sniff, stops the browser from performing MIME-type sniffing, mitigating MIME-type security risks. Strict transport security forces browsers to use HTTPS for all subsequent requests, improving confidentiality and integrity by preventing man-in-the-middle attacks. Secure cookies. Cookies are essential for managing user sessions in web applications. However, they often contain sensitive data, making their security paramount. The secure attribute in cookies ensures they are sent over HTTPS, reducing the risk of interception by an attacker. This line of code demonstrates how to set a secure cookie with various attributes for enhanced security. HT-only restricts access to the cookie from JavaScript, mitigating cross-site scripting, XSS attacks. Secure ensures the cookie is transmitted only over HTTPS, protecting against man-in-the-middle, MITM attacks. Same site controls whether the cookie is sent with cross-site requests, where strict completely blocks it from being sent with any cross-site usage, adding another layer of defense against cross-site request forgery, CSRF attacks. Combining these attributes makes the cookie more resilient to common web vulnerabilities. Public Key Infrastructure, PKI, and Certificates. Public Key Infrastructure, PKI, is a set of roles, policies, hardware, software, and procedures needed to create, manage, distribute, use, store, and revoke digital certificates. PKI is essential for secure communication over the Internet, ensuring the confidentiality, integrity, and authenticity of the data being transmitted. In this simple code snippet, we're using Node.js's crypto module to generate a pair of RSA keys, a public and a private key, which can be a basic part of a PKI system. The generateKeyPairSync method creates these keys. The public encrypt method encrypts some data, hello world, with the public key, meaning only the corresponding private key can decrypt it. This demonstrates how PKI can be used to ensure data confidentiality. The private decrypt method then decrypts this data using the private key, showcasing data integrity and authenticity, as only the holder of the private key could correctly decrypt the message. This code exemplifies basic operations of PKI and its significance in securing data transmission. OAuth and JDE for authentication authorization. In modern web applications, securing resources and managing user identities are crucial. OAuth provides a secure and efficient way for users to grant websites and applications access to their information without sharing their credentials. JSON Web Tokens, JDE, on the other hand, allow the secure transmission of information between parties as a compact, self-contained JSON object. Understanding how to implement OAuth with JWT for authentication and authorization is essential for developers. The code demonstrates a basic usage of JWT for verifying a user's token as part of an authentication system. Here, JSON Web Token package is used. The authenticate function takes a token and uses jw.verify to check its validity against a secret key. If the token is valid, information about the user, encoded in the token, is accessible via decoded. The function logs the user's username to the console and returns true to signify successful authentication. Conversely, any errors during verification result in logging the error and returning false, indicating authentication failure. Understanding this process is vital in implementing secure authentication and authorization strategies in web applications. React, component lifecycle, context, hooks, high-order components. React is a popular JavaScript library for building user interfaces, particularly single-page applications. It allows developers to create large web applications that can change data without reloading the page. Key concepts in React include component lifecycle, context, hooks, and high-order components. This code demonstrates several core React concepts. The useState hook allows us to create stateful functional components. MyComponent declares a state variable count and provides a way to update it. React's Context API, createContext, useContext, facilitates prop drilling avoidance by allowing count to be shared directly with myChildComponent without having to pass props through intermediate components. This serves as a practical example of using state, context, and hooks in React to manage and share state in a more efficient way. View, view instance, components, directives, view router, Vuex. The view instance serves as the heart of every view application. It is created by instantiating the view class, providing an options object that specifies data, lifecycle hooks, and methods. Here, a new view instance is bound to a DOM element with the ID app. It defines a data property named message, accessible within this instance's scope. When data changes, the view automatically updates, demonstrating Vue's reactive nature. Angular, modules, components, services, RxJS, Angular material. Angular is a platform and framework for building single-page client applications using HTML and TypeScript. Angular is written in TypeScript. Its architecture is based on certain fundamental concepts. In this example, app module is the root module that tells Angular how to assemble the application. It needs to import ng module from Angular/core to be recognized as an Angular module. Browser module is imported for running an app in a browser. App component is declared in declarations, indicating it's a part of this module. Imports array includes browser module needed for launching the app in a browser. No services are provided in this example, so providers array is empty. Finally, Bootstrap array lists app component as the startup component that Angular creates and inserts into the index.html host web page. Node.js modules, async programming, express.js, handling databases. Node.js modules allow you to break up your code into separate files, making it more manageable and reusable. Each module can export objects, functions, or variables to be used in other files. In this example, we import the HP module using require, allowing us to use its createServer method to create an HTTP server that listens on port 1337. When a request is received, it sends back a response with Hello World. Webpack and module bundling. Webpack is a powerful module bundler and build tool for modern JavaScript applications. It allows developers to bundle their JavaScript files and assets, such as CSS and images, into a single output file. This is especially useful for large applications, as it helps reduce the number of server requests and optimizes loading time. In this Webpack configuration, we define an entry point, /index.js, where Webpack starts the bundling process. The output property specifies the location, dist folder, and the name of the bundled file, bundle.js. Module.rules are used to define loaders that transform the code before it's added to the bundle. Here we include rules for CSS files, using style loader and CSS loader to bundle any CSS imports found in JavaScript files. This configuration lays the foundation for modularizing front-end assets and optimization. Babel and transpilation. Babel is an essential tool in modern JavaScript development, allowing developers to write next-generation JavaScript code that is then transpiled into backward-compatible JavaScript code. This process makes it possible to use new language features while supporting older browsers and environments. In the provided code snippet, an arrow function greet is defined, which takes name as a parameter and returns a greeting message using template literals. This represents modern JavaScript syntax that may not be supported in older JavaScript environments. Babel would transpile this code into a function expression or function declaration, which are widely supported, ensuring the code runs correctly across different environments. After transpilation, the usage of template literals and arrow function would be converted to older syntax, making the code compatible with older browsers. Testing libraries, Jest, Mocha, Chai. In modern JavaScript development, testing libraries play a crucial role in ensuring code quality and reliability. Three popular options are Jest, Mocha, and Chai. Jest is known for its zero configuration approach to testing, making it extremely beginner-friendly. Mocha offers more flexibility and requires manual configuration, while Chai is an assertion library that works well with Mocha, providing a range of functions to express your tests in a readable manner. The provided code shows how to test a simple sum function using Jest and then Mocha with Chai. In the Jest example, the test function defines the test case, and expect along with .to_be verifies the output. In the Mocha and Chai example, describe groups related tests, it defines a test case, and Chai's expect with .to.equal asserts the outcome. Both examples aim to ensure the sum function works as expected by checking if the addition of 1 and 2 equals 3. TypeScript, basic types, interfaces, classes, generics. TypeScript is a superset of JavaScript that provides strong typing through its type system. Here, we'll briefly touch upon basic types, interfaces, classes, and generics, essential concepts for robust TypeScript development. In the provided code, we define an interface person with two fields, name and age, which illustrates TypeScript's capability to enforce object shapes. Next, a class employee implements this interface and adds an additional field position, showcasing class-based inheritance and implementation in TypeScript. Finally, a generic function, logPerson, is demonstrated, leveraging TypeScript's generics to accept any object that extends person, ensuring type safety while maintaining flexibility. This example encapsulates how TypeScript integrates basic types, interfaces, classes, and generics to enhance code robustness and maintainability. State management, Redux, MobX. State management libraries like Redux and MobX provide a structured way to manage state in large applications. Redux maintains the application state in a single immutable store, following a unidirectional data flow. Actions are dispatched, processed by reducers to return a new state. MobX, on the other hand, uses observable states and reactions to achieve reactivity, promoting a more flexible and less boilerplate code approach compared to Redux. In the Redux example, the createStore method from Redux creates a store that holds the complete state tree of the application. The reducer function specifies how the state changes in response to actions sent to the store. Each call to store.dispatch sends an action, triggering the state update. Store.subscribe allows to listen to state updates. Unlike Redux, MobX would involve defining observable properties and actions directly on state objects, reducing boilerplate and improving readability for many use cases. Choosing between Redux and MobX largely depends on the complexity of the application and the development team's preference for explicitness versus minimal boilerplate.